its quantitative level is now, I think, much better understood. There's a lot of work we heard from Sarah Bridle and others yesterday about the intrinsic alignments, and again, I'll come back to that a little bit at the end of this talk. Finally, if I go to the strong lensing, obviously there's a lot of this. That basically is defined by having multiple images. The one aspect of this I want to just sort of inspired, if you like, this work is the prospect of measuring the Hubble constant with a time delay. Sherry talked about this on Monday. In this particular system that we've been playing with now for 15 years, we've got a lot of data on and thought a lot about. There's a relatively sophisticated modeling technique. It's a lens that has many positive features to it and some complications. And the bottom line is, if you fix the world model, you don't allow that to float, then the Hubble constant is measured to about 5% precision, according to this method and with the assumptions that are made here. And if you follow this roughly as a measurement, then you're now at the point where we believe that the accuracy of this determination is limited by the sort of weak lensing, the stuff along the line of sight. So that's what really got into this, and this is one of the spectra that was taken to get the velocity dispersion of the galaxy, which breaks the oh, I was going to show this, yeah, which breaks the mass sheet degeneracy. And then here's Chris Fastnack's monitoring of the radio. It's going. It was going before. Never mind. Okay, this is the monitoring of the radio variability, which gave the accurate time delays. Anyway, that's a sort of by way of introduction. Now what I'd like to do is to talk about weak lensing, or more generally, I suppose, just ray propagation in inhomogeneous universes. And this has been discussed many times in the literature. In fact, it goes back a long way to the 60s. There were many famous people in the 60s who thought quite hard about all of this, and it's well worth going back to, here's a list of at least some of them, reading the papers, so much of what I have to say was well known to these people at that time. This was in the 70s, but again, it's a little similar to what I have to say. Actually, the paper by Penrose is about something totally different, but the formalism is very similar to what you need for weak lensing. It's a curious thing. Anyway, the idea is the following. Let's imagine that we're the observer O, and we're going to have a null geodesic congruence that's going to emanate from us. It's in the scholastically correct way, it's going to propagate backwards in time. Apparently, I think there's still maybe a majority of people who believe that vision works that way. But we can do this in optics just fine. And there's some sort of angle theta at the observer following the usual convention, and then take the proper separation of an individual ray in this congruence, this bundle of rays, call it psi, and that clearly maps onto theta there. And it goes through this inhomogeneous universe, and they sort of wander apart and maybe come back together again. I'll use units in which G equals C is equal to H naught. I will not yet set pi equal to 3/8, but that I hope this is to be transparent. So if you go far enough along this ray, then eventually you'll come to a first focus where these rays will cross. That is a point that is tangent, of course, to a caustic, and there may be subsequent foci beyond that. As soon as you reach that point, you're then in the strong multiple imaging, strong lensing regime. So that's so what we're talking about in weak lensing is before you've got to that point, you're interested in sources that are not that far away. Now, the first question to ask is, what is the relevant distance measure to use along that ray? And there are many that spring to mind, of course, but the one that is relativistically correct is the so-called affine parameter that is used in the geodesic equation for photons, and basically it's defined as a constant of proportionality, if you like, between an increment of the 4-vector displacement in space-time to the 4-vector momentum, or equivalently k-vector here. And this is, if you like, a tangent along the ray, and it's parallel propagated along the ray. That's what the null geodesic equation means. So basically, this is the definition up to an additive and multiplicative constant of an affine parameter, and that's the sensible, formal, independent variable to use. And the natural choice to use in this context is just the integral of the time in the frame in which you're working here, anywhere locally, times the ratio of the frequency that the observer measures to the local frequency, so in that particular frame. And this is sort of formally correct, but if you just imagine a homogeneous reference universe that's next door to this, that has the same average density, and otherwise the same properties and same dark energy and so on, then the errors in using that homogeneous universe are of order the Newtonian potential and are ignorable at the level at which we're working here. If you do that, and then consider the differential equation that relates this transverse displacement to affine parameter measured along the ray, then it has a very simple form. Again, this is not always apparent in the literature. It's just like a simple harmonic equation. It relates to the Ricci scalar here, upper k vectors, and then if you use the field equations, then all it depends on, and I apologize for the repeat of W, but the enthalpy density, which is the energy density plus the pressure, remember C is equal to 1, minus 4 pi W over the scale factor A here, times psi. So it's like a sort of simple harmonic, modified simple harmonic equation. And so if you know the enthalpy along the line of sight, and if we just look at a congruence where there's just, and I'm doing this deliberately for this purpose at the moment, where there's just pure convergence, there's an extra term if there's shear there, but I'm ignoring the shear for the moment. If there's just pure convergence, this is all you have. And the conventional angular diameter distance will just be the quotient of the proper displacement to the angle subtended at the observer. So in homogeneous cosmology, actually I should just go back and make one point, this, if you allow me to believe in a cosmological constant, then the enthalpy of the cosmological constant is 0, it's identically 0. So don't believe that W is minus 1, it's actually 0. That's a joke. So all you're left with, if you believe it's cold dark matter, there's not some mysterious hot component, or you're sensitive enough to care about radiation or neutrinos, then it's just going to be the matter density with essentially negligible pressure. Just to make a point of reference about the kinematic, there's nothing new or original here, this is well known. If you instead replace the proper displacement perpendicular to the ray by a co-moving displacement, which just means dividing essentially by the scale factor, and you take the radius along the ray, which is then going to be d lambda over a squared, this, and then just essentially just all still geometry actually, then the equation becomes the even simpler second order differential equation, where k is this trichotomic variable, minus 1, 0, or 1, depending on the nature of the curvature, and R0 is the current scale factor. And it's as simple as that in the Friedman, Roberts, and Walker universe. And of course, if we have, and this is the case I'll be interested in, a negatively curved universe, an old-fashioned open universe, then we have the science solution which everybody is quite familiar with. So this is an equivalent statement to before, and I guess these connections are important because it doesn't, if you know exactly what the matter and the pressure, what the matter density and the pressure is along the line of sight, and it's isotropic, there's no shear part there, None of this is ambiguous. You can use any of these formalisms and you should always get the same answer for anything you measure. So, but this is a sort of connection, but I want to didactically make this connection here to curvature, because I'll come to that in a moment. Okay, let's do the strong lensing thing and care about time delays. The time delay relative to a reference ray, so here's the observer, there's the source if you like. The time delay can be expressed in this form.